Welcome to Playing with Junk again. This time I'm talking about reel-to-reel tape backup systems. Or, well, system is a little bit too much, just reel-to-reel computer tapes. And you probably know this kind of tapes from old movies where they are big as an entire rack, consumed kilowatts of power, and of course the newer models have also been a little bit more compact, like this one. It's a Digital TSZ07. Although it is not manufactured by Digital, it's just rebranded. It's a Cypher M995. So that's the latest version of this kind of compact tape. Well, no, that was not the name. It was a streaming tape. And you can see why it is called like this, because it writes a stream of data to the tape without starting and stopping the tape for every single data block. Now this one here is only in a diagnostic mode. It's a tape shuttle test. It spins 2 seconds forward, 1 second backward. That's just a mechanical test. You may already have noticed that the tape path here is a little bit weird. It goes from the right side here across the head, which is here, to the left, then goes back here, then here's the take-up roller, the take-up hub, and also the cover looks a little bit strange with all these holes and grooves and stuff. The purpose of all this is it's an automatic tape loader, and I will show you now how that works. So normally the black door here is closed, so you cannot see what happens inside. And if the cover is open, it doesn't work automatically, so I have to help a little bit. So the first thing is to open the front door here, slide in the tape. Normally this is mounted in a rack with other devices on top. Close the door, press the load button. Now it says that the door is open, so I have to enter code 45335. No, that's the wrong one. 455335. Yes. Now I can operate it with the door open. Press the load button. And the first thing is it will lock the tape on the supply hub with these 3 fingers here. Then it starts moving the tape around, and normally the airflow guides the tape here back to the take-ups reel, and that's it. And when the tape gets stuck between the take-up reel and the tachometer sensor here, which measures the tape speed, then it just winds up a couple of turns of the tape, and that's good enough. Well, and then you're asking yourself probably, how does the tape sense the beginning and the end of tape? There is no mechanical stop. If you rewind too much, it will simply unwind the tape here. Well, there is an array of sensors. It's in fact 2 sensors. One is a photodiode and one is some kind of LED. One of these sensor pairs looks at the upper part of the tape, and one on the lower part of the tape. And then when the tape moves, you will see a silver mark here on the tape. That's the begin of tape, which is sensed by the upper sensors here. And of course the end of tape has a similar marking, but on the lower part of the tape, which triggers the sensor below, and the tape knows that's the end of tape, and it has to rewind or stop and tell the system reaching end of tape. Well, when we are looking here, we have two things to see. First of all is a tape cleaner. That's two glass blades here. They are relatively sharp, and the purpose of this is to scrape away some dirt that sticks to the tape, dust, grains of sand or whatever. It just scrapes them away from the tape so that the tape head, which is here, does not get damaged. Now the tape head consists of three parts. First, this black part here is the erase head, which is only one head for the entire width of the tape, so it erases all the tape in one moment. Then we have 2 times a head array with 9 heads stacked on top of each other, so you're writing 9 tracks at once. The first one is the record head, and the second one on this side is the play head or the read head. And the purpose of this is clear. If you have written data, you can immediately read it back to check if everything is written correctly. And if it is not written correctly, it will rewind the tape and try it again up to 16 times here on this model. And then if it has no success, it will simply stop and report an error. One question is, of course, why is it 9 tracks? I mean, 8 bits is a byte, 16 bits is 2 bytes or a word. Why is it 9? So the answer is simple. You have 8 data tracks and 1 parity tracks. Now, what's parity? Let's say you write 0, 1, 0, 0, 1, 1, 1, 2, 3, 5, 6, 0, 1. Okay, that's 8-bit. Parity track 1 to 8. Parity is something simple. It's an error correction or an error detection. You simply count the number of ones, which is 4 in this example, and that's an even number. So another example is 1, 0, 1, 1, 0, 0, 1, 1. Here we have 5 times the number 1, which is an odd number, so the parity bit will be 0, and so on. So the parity bit is checked for every single byte that is written here. What happens if we have a read error? For example, if we read a 0 instead of the 1. We see the parity is 0. We must have an odd number of ones, 1, 2, 3, 4. That's something wrong. That is okay. What happens if 2 bits are read wrong? For example, a 0 instead of a 1. It could also be the other way around. 1, 2, 3. We have an odd number of ones, so parity says this is okay. And that's the problem. A double bit error you cannot detect with a single parity bit. But it seems that this method of checking the parity is good enough for this kind of tape, so in most cases. And the problem is you don't only have one single byte that is wrong. If there is a bad spot on the tape, you have all the next bytes with errors too, and this will certainly trigger the parity error here. Then the tape tries to rewind, read it again. If the same errors exist, it will stop, report the errors to the system, and that's why it has 9 tracks. Unloading the tape is as simple as loading, or even simpler. You press the unload button, tape will rewind until it detects here that no tape is in path, and it stops. It unlocks the hub here. Okay, let's go into detail. I always like this kind of tapes for their simplicity, especially those from the company Cypher. They had some very clever details. For example, here the sensor, the end of tape, begin of tape sensor. As you remember, it senses the begin of tape with the upper LED sensor pair here. It senses the end of tape with the lower pair, and here on the other side, you can see that is a little mirror, is a piece of aluminium foil. If no tape is in the path here, both sensors will get the signal that is reflected from here, and that means if both sensors get this signal, there is no tape in it. So no sensor means tape somewhere in the middle of the tape. One sensor means end or begin of tape, and if two sensors see a reflective foil, no tape. Simple, with only 2 diodes and 2 LEDs. Then here is another trick. You see this groove here, that comes from earlier models. They had an arm that was swinging like that, with the roller here attached to this arm and the spring. So they measured the tension of the tape with this mechanical device. If you pulled the tape to one side, the arm will move to this side and makes the take-up hub here to roll or unroll more tape. So this arm simply said how much tape has to be supplied or taken up, and it also made a constant tension of the tape. So they replaced this unit. They made here this plastic cover that is just for the airflow, and instead of this moving arm, they had a fixed roller here with a tiny little pressure sensor underneath. So this is only sensing how much pressure from the tape gets to this roller. This is of course a little bit a more modern version than a moving arm with a capacitor plate that is moving between 2 pieces of sheet metal. This is a purely electronic way, well, more or less. It measures the deflection here of this aluminium part with some glued resistors on it, but it has less mechanical parts that can fail, and probably it is a little bit more accurate. Then we have another sensor here, from here to here, that simply detects if the tape is unrolling from the spool here, and if the tape gets in pass here, this supply hub here will continue to supply tape until it is fed to the take-up roller here. There is another arm which has a rubber roller here. Probably you can see that. And inside the arm here is an optical sensor. There is a glass disc with stripes, which is detected by an optical sensor, and that measures the speed of the tape. So we measure the speed of the tape and the tension of the tape, and that's almost everything we need to know. Then the heads, I already explained what they are. You can see the connections, one ribbon cable for the read head, one for the write head, one for the erase head, which is only a 2-wire cable because the erase head is on or off. It doesn't need any special signals here. And here is the button that detects if the cover is open or not. There is, of course, a notch here that presses the button here, and if the cover is closed, you can press the load or unload button. So every movement of the tape is prohibited if the cover is open. That's a safety measure, because well, it's maybe a little bit dangerous if this thing runs at high speed, if it rewinds and you grab it with your finger inside. Okay, let's have a look inside. We first have to unlock the 2 screws here, and then we lift the entire mechanism up. There is a gas pressure cylinder here with a safety lock here that locks in. You probably heard it when I moved it up. We see a power supply with a fan. That's the big fan with the air ducts that moves the air. It blows air in on the front, it sucks air out here, and that's the channel where the exhaust air comes out, because the entire air mechanism here is also used for cooling. Then we have a big board in the front, which is the servo board that controls the 2 big motors, which are here, by the way. So they're quite big enough to make an electric bike, or big enough to use them for a wind power station or something like that, if you like to build such things. If we look up, we see another board. That's the preamplifier for the read and write head. It has a ribbon cable down here, goes to the read and write formatter board here, which does all the encoding. So, for example, you cannot write a series of zeros on a magnetic tape without doing anything. So a 0 would simply be, well, nothing. And if you write 10 times nothing in one row, you cannot detect that when you try to read it back. So there are all kinds of encoding, like MFM. You know that from hard drives, they do the same. This one here has 2 encoding versions. The one is called PE, the other is called GCR, Group Code Recording. If you want to know how that works, there are Wikipedia articles about that. And then here, back here, is the CPU board, which has some nice and big Xilinx. I think that's some sort of FPGA, early FPGA chips. In fact, the whole unit here is a direct successor of the older drives, very famous, the Cypher M990 GCR drive, the first drive in a compact version that actually was able to write 6,250 bytes per inch on the tape. It was a massive machine, almost twice as tall as this one, had 4 full-sized boards in it, and they managed it to squeeze all that electronics more or less into the two boards here and the servo board here. So that was possible with the new FPGA chips, the field programmable gate array chips. So they simply copied all the old schematics into these chips and making everything much smaller. By the way, this machine here was not a rack model, it was a tabletop model, so it had this fashionable plastic housing. Normally it was just looking like that and had some rails here which made it possible to slide it into a standard rack. It's 19-inch wide, but here with the cosmetic cover it was called the tabletop model. Well, it also had some feet to stand on a table. Of course you need a big table for that. Then on the back side we have power connector, power switch and SCSI port. That's why it is called TSZ. The Z on deck peripherals always stands for SCSI. They had other letters for other kinds of interfaces. Then, because this is a bit an old-fashioned type of SCSI connector, we call it the Centronics connector, because the Centronics parallel interface had the same connector but a little bit smaller. I had to use all kind of adapters here to connect it to my Alpha server, which has a HD68 SCSI connector, 16-bit. But the good thing is, if you only need 8-bit, like here, you just leave the other 8 bits hanging around in the air. That doesn't matter as long as the bits you use are properly terminated. Okay, so let's have a look on the Alpha server 2. It's a DS20E. It has here 3 power supplies, but only 1 power plug. It already has the new style compact disc, so this machine is from the time when Compaq has already bought DEC. By the way, Compaq has bought DEC, so this is an Alpha server ES40 Compaq. This is a ES45. It came out maybe a year later, was already labeled with HP. Okay, then let's turn it on. That's the power button. We have a reset button, we have a halt button, which has a light that indicates that it is pressed. Normally it locks in, this one doesn't do that. And I only connected the serial port, so it is complaining that no keyboard is attached. My serial interface, my terminal program, you probably know that, PuTTY, it's free, it's the best you can get. Okay, there it is. Make some self-test. 666 megahertz, the CPU of the devil. Okay, halt button is in, auto action ignored, halt button is in, really? Okay. Well, that's because I pressed it. Auto action is a setup point that you can say what the machine is doing when you power it on. You can say it should go to the halt prompt, which is this environment here, or if it should boot automatically from whatever device you defined. So let's see, show device, and we have an MKB0 which is a TSZ07, that's my tape here. We have a network card, we have two SCSI cards, they are listed separately, the cards. We have a CD drive, and we have an IBM disk drive with 9 gigabytes. Okay. DVA, that's the floppy drive that has no ID, because the floppy doesn't report any ID by its interface. Okay, and one little plaything. There is a sound test here, and if you type that, you will hear this. That was the sound test. And because this server here has a graphics card inside, I connected a VGA screen and an old PS2 keyboard and mouse, and let's see how that looks like. Well, first here in the on the HALT prompt, in the HALT menu, there's not much different between the serial port and the graphics port, but a little bit later when we boot up, we will probably see how DEC Windows or HP Windows looks like. By the way, let's show the memory. 512 megabytes. That was quite a lot in these days. Well, not for this server. That was already in the time when you can have more memory. So boot is the command. That's the boot device, DKA0, which is stored in the setup. You can put there every boot device you want. Let's see what happens. I haven't started up this machine since quite a while. 1976 to 2003, yes, of course. Hewlett-Packard didn't know about VMS in 1976. That was purely a DEC operating system, but well, if you buy it, you can rename it as you want. Starting network, starting all kind of stuff, and now it's switching to the graphical interface, and that's something you don't get on the serial terminal. My username is system as always. Oops, we should use the right keyboard. German keyboard on a US system doesn't work. System is the system manager account, is like root on a Unix system. Okay, I don't have a password here, it's only a lab server. And we have a window with our text terminal inside here. Then we have, of course, we can open more text windows. We also have a file manager. So this is the CDE desktop. You can still have that for Unix system. It's a desktop that is independent from the operating system. You can have it for all kinds of operating system. Various Unix versions have that. Well, and that's the version of VMS. Okay, let's show tape, show device MK. We have a MKB0 B stands for the second SCSI controller, 0 is the unit number, M stands for magnetic tape, and the K here stands for the SCSI interface. And DS20E, it's just a node name, and the dollar is something to combine the two names. So the next step would be init MKB0. We don't have to write the full name in this case, except that where is my... I hate it when the keyboard is wrong. No, it seems that shift button is not working. Okay, oh no, there's the column. Label test. And I forgot to set the unit online. Press the online button, yes. And now it starts moving. And the problem is now this tape has, well, a problem. It doesn't write correctly. I don't know if it reads, but for some reason it cannot write. And on the screen it looks like that. Now it tries to rewrite 16 times, and then it gives up and reports a parity error. Okay, let's see how it looks on the tape side. Well, let's just try it again. Initialize tape, go, and the whole game repeats itself. And now it starts writing and goes forth and back, tries to repeat, and it still gets errors. I don't know why. I already tried to recalibrate the heads. Everything is automatic, everything works, but it doesn't work together with the system, so I don't know what's happening here. And for the end of the video, I want to show you some highlights from our basement, where we keep all the old machines for a while, because we still have customers using this. Maybe not that PDP-11 here, but more likely a digital Alpha Server 4100. Could be around somewhere, I don't know, maybe not one of our active customers, but certainly possible that we get a call someday where someone seeks spare parts. The old DL380 from the video before. We also have the Microvex 3100 model 98, this time from digital, of course. Alpha Server 800, model 5/500. The 500 stands for the megahertz it has. 500 megahertz. That's it. Workstation Alpha Station 200, 166 megahertz. Some old Dell Optiplex PCs. I think we can scrap them in a short time. We haven't used these types for long, and I don't think we will use them again. This one is quite exotic. It's an Alpha Server, but in an industrial case. So it's made by a company, I think it's called ETM. It's the ETM31. It has a Alpha processor board inside. It has a standard PC power supply. And it was used by the Swiss railway company for, well, I'm not sure In fact, I don't know what they use it for, but well, we still keep it because if you need spare parts for those, they are very hard to get, and if you get it, they are extremely expensive. Someone asked me if we also have the titanium-based models from HP, for example the RX 7640. Well, yes, we have a couple of them in all different sizes. We also have old Sun stations, Spark Station, Ultra 2, the old servers, a little bit newer servers, some blades. And that's the view on our ramp where everything ends. Some people say that we are a recycling company. That's not true. We are a company that provides maintenance for bigger companies. But we of course do recycling of the old components we get back or we don't use anymore. Here we have some battery packs from a huge UPS. We have a pallet full of cables, switches, all kind of stuff. And here some printers, PCs, all kind of, sometimes from private households, sometimes from office. It doesn't matter, we can give them away for free. I mean, they will collect it with no charge because we pay here in Switzerland when we buy a new device. We pay for the recycling in advance, so no problem about that. A lot of space here to fill, and when they are full they get collected and we get new ones, empty ones, and the cycle begins from the beginning. Okay, that's it. Thanks for watching.